Hey everybody, this is Paul. In this tutorial I'm going to be doing a proof by mathematical induction. And so in this tutorial I'm going to prove that 1 plus 3 plus 5 plus all the way up to some 2n minus 1 term, all of that is equal to whatever that n was squared here. So what exactly does this notation here mean on the left hand side? So if you want to think about each of these terms, the 1, the 3, the 5, each of those are all some 2n minus 1 term. So how exactly does that work? Well, this first term, the 1 right here, this represents the term where n is equal to 1. The 3 here represents n equals 2, and the 5 represents n equals 3. And so to say it goes all the way up to 2n minus 1, well, that's just for some arbitrary n. N could be 6, n could be 25. We can pick whatever we want for n, and whenever that number is, we add up all of the n1, n2, n3, n4, and all the way up to 25 if that's what we were going to, and then we would plug in that 25 for the n squared here. So how exactly is 1 representative of the 2n minus 1? Well, since n equals 1, we have 2n minus 1, and n equals 1 for that first term, so we have 2 times 1 minus 1, and that is equal to 1. So that's how we get 1 for our n equals 1 term here. So then the n equals 2 term here, we have 2 times n minus 1, but this time 2 times our n here is the 2 this time, since we're n equals 2, and then that minus 1 is equal to 3, and so that's how we get 3 for our value here for this n equals 2 term. And you can do the same thing here and find that when n is equal to 3, we get the value 5. And so that's basically what all this means. That's what it means to go up to 2n minus 1. It really just depends on the nth term, how many terms we're going to. And all of those added together are equal to n squared. So let me just go ahead and get rid of all this stuff that I just drew right here. So now that I've got that explained, let's go ahead and begin the mathematical induction proof. So the very first step in the mathematical induction proof is what we call the basis step. And so for the basis step, we're basically going to look at the most simple case that we can come up with and make sure that this statement is true on both the left hand and the right hand side. So we're making sure that the left hand side is equal to the right hand side for the most simple case. And so for the basis step, we're going to be looking at the case where n is equal to 1. And as we mentioned in this part I just erased here, the n equals 1 term on the left hand side is equal to 1 right here. So we'll just go ahead and write that down. So for the left hand side we have the value of 1, and for the right hand side we have n squared. Well, n equals 1 would be 1 squared. So on the right hand side we have 1 squared, and 1 squared is equal to 1, so we simply have 1 is equal to 1. So for our basis case we have 1 equals 1, and that is a true statement. So now that we've shown that the basis case is valid, let's go ahead and move on to the next step of the mathematical induction proof. So the next step is what we call the induction step. So I'll just put that up here. So this is the induction step. And so for the induction step, what we're going to do is we're going to choose some number for n, and we're just going to have that be some arbitrary value. So we're going to go up to n is equal to some value k, and k can really just represent any number we want it to. And we're going to assume that that is true. So I'll put assume true here. So we're going to assume this is true. And what exactly we're assuming true is we're going to assume that 1 plus 3 plus 5 plus all the way up to some number where n is equal to k, so that would be 2 times k minus 1. We're going to assume that that is equal to k squared. So what we're doing here with the induction step is we're just basically rewriting the entire statement here, but where there's an n, we're just going to replace that with a k. So we have n here, we have k here, we have n squared on the right hand side, and we have k squared on the right hand side. So k is just representing some arbitrary number that we want to go up to, and we're just going to assume that is true for now. So I'll go ahead and put this in a box. So the next thing we're going to do is we're going to prove that this statement is true, and we're going to prove that it's true for k plus 1 based off of this assumption right here. So let's go ahead and write that down. we're going to show that this is true. And by this I mean this statement up here that we're trying to prove. We're going to show that it's true based off the assumption that it's true to go up to some value where n is equal to k. And we're going to show it's true for the value n is equal to k plus 1. So if you think about this, we proved that it was valid for the n equals 1 case, for the most simple case, and then we're just saying we can go up to any number we want. And so if we think about it, we could have just gone up to number 1, and then if we prove that it's true for k plus 1, then that means that we've proved it for the n equals 2 case, and then if we've proved that, then n equals 2 could be our k over here, which means that if we can show that it's true for n equals k plus 1, then we've proved the n equals 3 case, and so on and so forth. And so showing that the basis case works, and then assuming that it's true for any k we choose, and then based off of that assumption, if we can show it's true for the next case, then we've proved that this is true for any n value that we want, assuming that n is an integer with a value 1 or greater. So now we're going to go ahead and show that this statement is true for n is equal to k plus 1, based off of the assumption that we made in our induction step here. So the way we do that is we just simply write 1 plus 3 plus 5 plus, and then we're going to go all the way up to the n equals k term. So 2 times k, placing k where n is here, minus 1. So this right here would be for n is equal to k, but we want to show that it's true for n equals k plus 1, so we need to add that next term. So we can do that by saying plus 2 times, and then instead of k, we're putting k plus 1 here where n is. So we'll go ahead and put k plus 1, and then that's minus 1. And then we're saying that that's equal to the right-hand side, which is n squared, but in our case, we're doing k plus 1 squared. So we'll put k plus 1 squared. So now if we can show that the left-hand side is equal to the right-hand side, then we have completed the mathematical induction proof. So now if we notice here, this part right here is equal to the left-hand side of the assumption that we made in our induction step. And since we're assuming this is true, we're assuming the left-hand side is equal to the right-hand side, we can replace all of this stuff right here with k squared, which is what we have right here in the right-hand side. Since this is right here, and this, according to this assumption right here, is equal to k squared, we can just replace all of this stuff with k squared. And so then all we have to do is we just need to add that to the 2 times k plus 1 minus 1 and see if that's equal to k plus 1 squared. So this part right here, 2 times k, is 2k, and then distributing the 2 times the plus 1, so this would be plus 2, and then we have the minus 1 over here. So is that equal to k plus 1 squared? And k plus 1 squared is the same thing as k plus 1 times k plus 1. So now we have k squared plus 2k right here, plus 2 minus 1. A 2 minus 1 is a positive 1. So on the left-hand side we have k squared plus 2k plus 1. And is that equal to k plus 1 times k plus 1? So for the right-hand side now, we have k times k. K times k gives us k squared. And then we have k times 1. K times 1 gives us a positive k. And then we have 1 times k. 1 times k is a positive k as well. And then we have 1 times 1. And 1 times 1 is equal to 1. So then right here, k plus k is equal to 2k. So now rewriting this term right here, we have the plus 1. And then this term right here, we have k squared, and then we're adding that to the 2k here. And so now on the left-hand side, we have that k squared once again, plus 2k, plus 1. So you can see that the left-hand side is exactly identical to the right-hand side. And so now we have completed the mathematical induction proof. And so we have proved that 1 plus 3 plus 5 plus some 2 times n minus 1 is equal to n squared. And we did that by mathematical induction. So anyway, thank you guys for watching. Have an excellent day. And if you haven't already, don't forget to subscribe.